Okay, hello everyone. My name is Gong. I am a PhD student from Cooperative Robotics System Lab at Arizona State University. I will talk about temporal spatial inverse semantics for robots communicating with humans. Today we are seeing many robots entering humans' life. Their application domain spans from search and rescue, industrial manufacturing, to education and so on. However, one specific role for robots that we are yet to see is the role of a human teammate. Teaming is a complex cognitive process that involves many aspects, such as shared mental model, team situation awareness, team cognition, which contribute to the transparency between team members. In human-robot teaming, such transparency between teammates requires not only the robot understand the human's intent and behaviors, but also the human understand the robot's intent and behavior. Since we cannot expect the human to maintain complex model of the robot to infer about their intents, the robots are expected to signal their intents and explain their behaviors. So signaling of the robot intent can be achieved either explicitly or implicitly. Explicit communication can be performed using natural languages and visual cues, while implicit communication is achieved by legible motions, communicative actions, and explicable task plans. In this work, we are interested in communicating explicitly, especially using natural languages. In particular, we will look at some of the remaining issues with signaling using natural language. Okay, next, we motivate our work by walking through a demo to illustrate the main idea of this paper. So this is an indoor domain. The task for the robot is to help the human sort objects on the table and store them into a storage box. Meanwhile, the human is working alongside the robot nearby. At some point of time, the human finds that there is another plastic bin that needs to be stored. He puts it on the table and informs the robot.
I have another thing for you.
Then the human may expect the robot to continue moving the remaining objects on the table. Consequently, the human may choose to sort objects in the storage box. In this situation, however, since there is not enough space in the storage box, the robot replans and decides to take out the plastic bin first to make more space. This could lead to a hazardous situation. In such cases, it becomes crucial for the robot to signal its intention to the human. The information for signaling here may include the action to be executed, the relevant object, and the robot's intention. To ensure that the signaling is precise, in this case, it is also important to make clear which object is to be manipulated. This can be achieved by referring to the object using the temporal context. Since the object to be manipulated was placed into the storage box in the previous step. So in this situation, the temporal context makes the reference to the objects very clear. Here is a sentence generated for signaling using our approach.
I will take out the bin which I just placed in order to make more space.
I got you.
The human is clear about what the robot is doing after the signaling. Sometimes using temporal information may be required since the situation would otherwise be ambiguous. Continuing with our scenario, in this case, the robot plans to put the cube on the table into the plastic bin it just took out. Due to the size of the cube, the robot cannot pick it up by itself and needs the human's help. Given that there are two plastic bins that are almost identical except for a small difference in sizes. The sentence that only refers to the bin for signaling will be ambiguous. Although spatial context may be used in this situation, using temporal context is more direct and easily understandable. So here is a sentence generated for signaling using our approach.
Please put the cube in the bin which I just took out from the storage box.
Okay.
The temporal context information helps disambiguate to clearly identify the bin to be used in this case. So our approach is called Temporal Spatial Inverse Semantics, TESIS. First of all, to search for an interpretable natural language sentence, we use generalized grounding graph to build a mapping between the groundings in the environment and the natural language constituents. Here, the phi is a binary correspondence variable for indicating the correctness of the mapping. To use spatial context information for disambiguation, a method called inverse semantics was proposed. To generate more effective signaling in complex environment, we further incorporate temporal context information from the previous states to help resolve ambiguity during signaling. We extend the graph using context-free grammar. The extended structure allows references to context information from the current and the previous states. We introduced a new metric H that incorporates the consideration of context information from the previous states. It is used to capture the probability that a human would correctly interpret the robot's signaling, similar to that in inverse semantics. To reduce the computational cost, we place a limit on the earliest previous state that may be referenced from the current state, bounded by a constant n. Furthermore, to simplify the sentence generated, we also limit the augmented sentence structure by a constant k. When generating a signaling for the current state, k out of n previous states will be selected. We search over all the groundings from the current and the previous states to find the sentence with the highest value of h. For example, in the scenario at the bottom, when k equals to 1 and n equals to 2, it means that we only allow the signaling to use one of the states from the two immediate previous states as its temporal context. So here's the search schema for TESIS. There are 3 levels. Level 1, given the desired action or object groundings, we search over the predefined natural language corpus to find the top M sentence candidates. At the second level, the sentences are extended by using the CFG sentence generator that allows references to the k selected previous states. At the third level, we search over all the groundings from both the previous and the current states to find the sentence with the highest value of h. To compare TESIS with inverse semantics, we evaluate our approach in an existing synthetic domain. The domain involves commanding a forklift to move different types of pallets around. There may be multiple pallets of the same type, and hence ambiguities are introduced. As an example shown in this slide, the target is to generate a sentence to request the human who is also operating a forklift nearby to lift the tire pallet shown in the red circle. As seen from the example, it is difficult to come up with a sentence to refer precisely to the target using only the current state information. The inverse semantics approach will only be able to refer the current state and generate a sentence like lift the tire pallet on the left. To incorporate the temporal information, we consider the changes of the environment state over time. When the previous state can also be referenced, shown in the example as t-1, our approach will generate a sentence like lift the tire pallet on the left, which was behind the trailer. For evaluation, we randomly generated environment states at previous time steps by moving objects to different locations. 3 evaluation settings were posted on the Amazon Mechanic Turk. One used inverse semantics. The other 2 settings used the TESIS with different k and n values. The result showed that both settings that use TESIS performs better than inverse semantics. In this work, we address the problem of signaling a robot's intent using natural language sentences by incorporating temporal information in the past. We formulate the human's understanding of the generated natural language sentence as a learning and inference problem by searching over multiple time steps. The evaluation results show that our approach can generate more easily understood sentences than the existing approach. Thank you.
Excellent talk, indeed. I just have a small question. Concerning the example, lift the tire pallet on the left, which was behind the trailer, something probably I couldn't understand well. How did you understand the lift and the behind the trailer?
Can I say again?
The lift, when you, the lift on the left. So how did you understand the lift, and how did you understand behind the trailer?
The left, on the left is from the perspective of the forklift, which is in the green box. That is not from the perspective of the human.
Mm-hmm.
And behind the trigger is in terms of the trigger, which is...
In terms of?
Yes, yes.
Sorry, I couldn't get this. In terms of
I cannot. The behind the trigger is in terms of the trigger over there, and the tire pallet is just behind that, which is based on the physical position of these 2 objects.
You mean locations?
Yes. Yes.
Okay, but so
So
I understand. So based on the location, I can understand how did you. But behind the trailer, okay. So you decide behind the trailer. Actually, this phrase has 2 parts: the trailer as an object.
Mm-hmm. Yes.
And the spatial relationship.
Yes.
So you had 2 modalities of information to understand in this phrase.
We used the generalized grounding graph to build a mapping between the groundings in the environment and the natural language. So for the spatial relationship, we also have like a place factor to model this spatial relationship in that framework.
A simple question. Have you grounded, trying to understand word by word or phrase by phrase?
Phrase by phrase.
Okay. That makes sense. Thank you so much.
So any other question or comment? Yeah, I have one quick question. Is there any case that this contextual temporal search result in a wrong decision?
Sorry?
Wrong decision, yeah. Incorrect decision.
Yes, yes. So that is why the successful interpretation rates of the generated request is only like 2/3. The result is not very good.
Can you give one some interesting example or what?
For example, for some scenario that one object is clearly at the right of the other object, but in our system will generate behind or front. Even sometimes we can generate on the right, exactly the opposite direction, opposite position of the exact spatial relationship.
Okay. Any comments or questions? All right, let's thank the speaker.